Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 5 Part B. Question 1 states, for a proportional controller and a third order transfer function 2 over 12 times s plus 1 cubed, create a Bode plot and find a value of the maximum stable controller gain, i.e. controller gain where the amplitude ratio is 1 at a phase lag of 180 degrees. So to start, we're going to go over to Google Colab, where I have already imported all our libraries and everything from the template provided. The first thing that we need to do is define our controller gain and our function. So our gain, we're just going to guess and say that it's 1.2. For our process GP, this was given to us as 2 over 12 times s plus 1 cubed. And so overall, this is going to be g, and we just multiply that together, so gc times gp. Now what we want to do is give ourselves some omega values, so we're going to call this ws, and we want this to be on a log scale, so np dot log space. And we want to go from -3 to 4, 100 steps. Next, what we want to do is substitute s with j omega. We're going to call this j omega. To do this, we need to convert from a SimP function to a NumPy, or a Python. So we can do SimP dot lambda phi, and then what we input is our omega values, and our substitution is g dot subs, and then we have the variable that we have now, s, and what we want to have, which is omega times 1j. And we want to evaluate this over all of our omega values. Next, what we want to do is identify our real and imaginary parts. We kind of went over that in Part A. So to do that, what we are going to have is Ri is equal to np dot real, gj omega, and then np dot imag for n gj omega. Now that we have our real and imaginary parts, we can calculate m. And this is from Part A, so we know that m is the square root of r squared plus I squared. And now that we have that, what we want to solve for is phi, or our angle. So phi is np dot unwrap, since we're using np arctangent. And this is imaginary over real. And right now this is in radians, so what we want to do is convert to degrees. So we're going to multiply by 180 and divide by pi. Now we are ready to plot, so we can say thing is equal to make subplots, and we want to have 2 rows and 1 column. Now we can do vig.add scatter for the first plot, and our x values are our omega values. Y is m, and this is for row 1, column 1. Our second plot, our x is also going to be omegas, but this time y is phi. And this is row 2, column 1. And now we have to go and change our axes. For the first plot, we want to do big.update underscore our x-axis, and for our top plot we want type to be log, and then dtig is equal to 1, and this is for row 1, column 1, since it's our first plot. And then I'm going to take this and paste it twice. Now this one we still want to be for our first plot. There we go, so we just change it to y-axis. The second one, our x-axis for the bottom plot, is in log. So to change that, we just have to make this row 2. And then finally, our axis, our y-axis, for our bottom plot is linear. So we want to say dtig is equal to 180 and assign it to row 2, column 1. And then just to make it look a little better, we'll update the layout. So width is equal to 500. Is equal to 600. Enter. And there we have our Bode plot. So to find where m is 1 at 180 degrees, we want to go look at 180 degrees on our bottom plot here, which is our angle, which is why we specifically made there be a tick for 180. So if we go across to 180, we find that the value is probably about 1.4. Now remember, our x-axis on both these graphs is the same, so all we need to do is go straight up to find what our magnitude is, our m value. So at 1.4, I can't quite hit those numbers right, but we're between 0.25 and 0.3. Which means that right now this system is stable since it's below 1, but we really want to find that value where m is 1. So to do that, we can go up here and start messing with our controller gain value. So we can up this to maybe 3 and see where we are. So we come back over here. Again, we're at about 0.14. We come up here, look for that value. We are closer this time, but not quite at 1. So we can up it one more time. Let's maybe put it at 4 and do the same thing. Again, between 0.3 and 0.5, so probably around 0.4. If we go up here, we could see that somewhere between those values you would hit 1, so we could approximate based on this that 4 is the controller gain at which m would be 1 when phi is 180 degrees. Now we can move on to question 2, which states, simulate the closed loop response of B1. So if we just go under here, we can create the variable for a closed loop function. We know that this is everything in the forward direction, so GC times GP divided by 1 plus everything in the closed loop system. In this case, we're going to say GC times GP, as we're assuming that the measurement is just 1. Now to plot, we need our t and y values, and to do this, we're just going to go sim, and our function is GCL. Our time input is lambda t, in this case it's just 1. Our number of steps, which is 1,000, and our step size, we're going to put at 0.5. Now to plot, we're going to say big is equal to make subplots. Big dot add scatter. Our x is t, and our y is y. And then just big dot update, layout, width is 600, and height, we put it 400. Now this is to be expected since we still have our GC at 4, which is we approximated from our Bode diagrams to be at that cusp of stability. And we can see that as these oscillations aren't growing or dying out. But if we really want to see if our original statement was true, that it was stable when we had GC at 1.2, meaning that m was less than 1, we can see that here as it kind of evens out. Next, we can move on to question 3. This states, determine the ultimate gain and ultimate period from B2 and use the Ziegler-Nichols method to determine the controller gain and reset time for a PI controller. Okay. So if we come over here, our goal is to use the Ziegler-Nichols method. And this method says that we are just going to keep adjusting that controller gain until we find where we are again at that cusp of stability. So where those oscillations are not growing or dying out. Luckily, we've already done this. So we can just come back here and change our controller to 4. And this is that ultimate gain that we were talking about. So that is KU. And set that as 4. There we go. And as far as the ultimate period, how you solve for that is you look at the difference between each peak from peak 1 to 2, from 2 to 3, and you just subtract and find the difference between those values. And so we're going to say that that is about 43. That's PU for the ultimate period, 43. And since we know what kind of controller this is, Ziegler-Nichols has already given us values for solving for the controller gain and the rest period. And for the controller gain, this value is 0.45, and we just multiply by the ultimate controller gain. And for the rest period, tau I, it is 0.83 times the ultimate period. Finally, we are ready to move on to question 4. This states, simulate the closed loop response of the PI controller in B3 to a step change in set point. Okay. So now we can come over here, and just like before, we need our GC, GP, and our closed loop. And I'm going to cheat a little bit and copy paste from above. So we can just take these functions here and our closed loop, since this is all part of the same system, we're just altering it a little now. The main change here is that we want to incorporate our controller gain as well as our step change. So this would be now KC times 1 plus 1 over tau I, S, since we do our Laplace of the step change. And now we are ready to plot this. And again, I'm going to cheat a little bit and steal what we already wrote there. And now we can see how this PI controller is able to stabilize the system.